Here it comes. Open this case. And here is today's restoration project. A 9 Wild Heerbrugg reversible level. Speaking of levels, you've likely seen them on the street. They're the ones mounted on tripods, aimed at a distant staff, taking measurements back and forth. Well, this instrument doesn't measure distance, but rather height. More accurately, it searches for an absolute horizontal reference line. Whether building high-speed rail, laying down roads, constructing factories, or building bridges, all these projects share one prerequisite. You must first find the level. But before leveling things out for others, we must ensure the instrument itself is level. Only when situated on a perfectly horizontal baseline can it accurately judge whether a target is too high or too low. So, structurally speaking, this level is essentially a high-power telescope, combined with a complete set of precision mechanisms designed to establish a true horizontal. Now that we have a basic concept, let's take a closer look at this 69-year-old level and see what makes it unique. Its biggest feature, as mentioned at the start, is its reversible telescope. This telescope can flip 180 degrees along its axis. This isn't for viewing convenience. It serves only one purpose: error calibration. After all, we know that every piece of machinery has mechanical errors. So, the engineers behind this level didn't try to achieve zero error. Instead, they made the errors predictable, repeatable, and by flipping the telescope tube, it reverses the direction of the error. Then, by taking the average of the adjustments, even though the error doesn't vanish entirely, a significant portion of it gets canceled out. This concept is known as systematic error compensation, and it was one of the most advanced calibration methods in the 1950s. Moving on to the next feature, it's one of Wild's most classic patents: the coincidence bubble level. As mentioned earlier, this instrument is essentially a telescope, paired with a precise leveling platform. And to check if this platform is level, you rely on observing the bubble tube, meaning you check the position of the air bubble inside. To make this observation more accurate and clear, Wild added a prism system to this tube. We'll get into the details of how exactly it works later. Right now, our master restorer, Ayaz, has already completed all the disassembly work. Next, Ayaz will begin this episode's restoration work, starting with this horizontal rotary base containing the central axis. First, he uses a paint stripper gel to remove the old paint from the parts. The reason for using a gel-type paint stripper here is so it clings better to the components, making the stripping process much more efficient. For this severely rusted bottom section, that doesn't require high precision, white corundum sandblasting can be used to thoroughly remove the rust. As for other areas that weren't fully cleaned, he uses a polishing tool for some light surface cleanup. For this specific restoration, Ayaz adopts a restore-as-you-assemble approach, so the treatment process for many parts is largely similar. I'll just highlight the key steps as we go. After a thorough cleaning, the next step is applying a 2-part epoxy primer, followed by a green top coat. As for the rusted inner ring at the bottom, he applies this bluing solution. For a cold bluing treatment, and with that, this horizontal rotary base is fully restored. Next, Ayaz will use this as a foundation, installing the restored parts onto it one by one. The part being installed now is a locking lever with a locking knob at the end. Of course, if you wanted to, you could just turn the body directly to rotate it. So, the main purpose of this lever is to help with coarse adjustments within a certain range. Additionally, this polished and nickel-plated locking knob provides a certain amount of dampening friction to prevent overshooting during coarse adjustments. Also, on this knob, there is a small set screw designed to prevent you from locking it too tight, which could cause excessive wear on the central axis. Where there's coarse adjustment, there's fine adjustment. The fine adjustment screw mechanism will be installed on this bracket that is currently being prepped. Similarly, this bracket will also get painted after a deep cleaning. Moreover, a universal circular bubble level will be mounted on this bracket to roughly check if your tripod is set up level. That's the round part being inserted right now. This particular piece, which has been sandblasted, polished, and cold-blued, it's not an oil hole screw for the central axis. It's actually the bearing block for the pitch adjustment screw. And this elevation fine-tuning screw will be installed on this square mounting base that houses the main rotation axis. This area has strict precision requirements, so aggressive rust removal like sandblasting isn't used here. Instead, gentle polishing is used for light cleaning. After that, the corresponding protective paint is applied, and it can be installed into its designated spot. As for the screws used to secure it, seeing how shiny they are, you can tell they've undergone nickel plating. Now, after tightening the bottom end cap, he can start working on the horizontal fine adjustment screw mentioned earlier. But before doing that, he needs to install this spring, which provides dampening and tension. This whole assembly of parts forms the fine adjustment mechanism. The treatment for this section is exactly the same: rust removal, polishing, and nickel plating. The reason it's designed in such a complex way, with both coarse and fine adjustments, it is quite simple. Under a 26x high magnification telescope, even lightly tapping the instrument with a finger will cause targets dozens or hundreds of meters away to shift dramatically in the lens. Therefore, all delicate adjustments must be handled by the fine screw, which provides steady, slow, and highly controlled movement. What's being installed right now is the fine adjustment mechanism used to regulate the elevation angle. Specifically, this section uses that previously installed bearing block as a base to lift this U-shaped mount sitting on top, thereby achieving pitch angle adjustments. Likewise, there's also a spring here to provide tension and dampening. Next up for restoration is the upper telescope assembly. Starting with the objective lens, you can see the glass inside is still very clear, with no issues at all. He just needs to mask off the lens and the threads, then sandblast both the inside and outside. The interior will also be treated with a bluing solution. As for the exterior, it will join the freshly polished main tube for primer and top coat application. This bearing is for mounting the telescope's focusing knob. However, this focusing knob assembly has a broken screw stuck inside. He needs to drill out the broken piece and tap new threads into the hole to fit a new screw. He is tapping an M25 thread here. With that sorted, he can finally reassemble this focusing knob unit. This focusing knob uses a gear underneath to drive the toothed rack on the focusing lens, moving it forward and backward. This accomplishes the coarse focus adjustment, looking just like this. And since there's coarse adjustment, There's certainly a fine adjustment mechanism too. This fine focusing ring is integrated with the telescope's eyepiece, which is currently being worked on. From this angle, you can see there are scale markings around the perimeter of the knob, and right in the center sits the eyepiece. Additionally, on top of the telescope, they thoughtfully included a mechanical sight, much like the iron sight you often see on firearms. Next to the telescope, this tube with two viewing windows is the coincidence bubble level we mentioned at the start. Even though there are two windows on top, there's actually only a single tube inside, and only one air bubble. These two windows are designed to work with the prism system mounted above them. It works like this. These two components make up the prism system we keep talking about. Through optical reflection, this system splits the image of both ends of the bubble, right down the middle, and sends it to a specialized viewing eyepiece. If the instrument hasn't reached true level, we'll see through the eyepiece that the two halves of the bubble are misaligned. Only when the two halves perfectly merge into one continuous bubble shape does it prove that the bubble is dead center, meaning the telescope's line of sight is perfectly horizontal. This method, compared to staring at a standard bubble level, trying to eyeball if it's perfectly centered, it's obviously much easier and much more accurate. You could say it elevates human visual judgment accuracy to an incredibly high level. What's being tightened now is the eyepiece we just discussed, used to look through the prism system. Of course, if you remove the prism system, this level indicator also functions as a normal bubble level. While the precision drops, the advantage is speed. A quick glance gives you a rough idea of its level, acting as a fast, coarse calibration step. So, to accommodate this basic viewing function, besides the prism system, this level, it is also equipped with a reflective mirror strip for direct observation of the bubble. As the mirror strip is installed, you can clearly see that the two windows on this side are completely open. And with that, the entire telescope assembly is complete. Next, it can be mounted onto the base. As for this cover plate with the logo, being the face of the instrument, it will get painted and then undergo ultra-fine polishing. Moving on, what we see here is the leveling baseplate. It might look like just a simple triangular bracket, but it actually bears the most critical task of the entire instrument, establishing a stable and reliable horizontal baseline. The base features a triangular layout, and at its three corners are three leveling screws. The operator simply turns these three screws, using them like miniature jacks, to slowly raise or lower the instrument's three support points, ultimately bringing the whole level into a perfectly horizontal state. Now, tighten the locking nut, and this antique 1957 Swiss reversible level. It is officially restored. By the way, the protective cases for such high-precision instruments are also very important, so I made sure to restore those as well. He even coated them in a visually striking and highly durable green hammer tone paint. Next, let's take a look through the lens to compare before and after the restoration. And that wraps up this restoration video. Thank you all for watching. That's all for today's episode. Thanks for tuning in. Goodbye, and once again, thanks for visiting Max's Restoration Realm. Bye.